Laser Technology: Principles, Types, and Applications. Prepared by engineer Adil Salih. The term laser stands for light amplification by stimulated emission of radiation. Since Theodore H. Maiman successfully demonstrated the first working model in 1960, the technology has scaled across multiple industries. A laser does not function like a conventional light bulb. A light bulb scatters chaotic, multi-directional light, whereas a laser operates as a highly engineered device that forces light into a strict, organized, and intensely focused beam. To understand how this works, we will step through the underlying physics, examine the mechanical types, and review specific industrial applications. Grasping the utility of this technology requires us to look past the external beam and examine the internal architecture generating the output. The mechanical precision of these systems allows them to perform on vastly different scales, from microscopic biological interventions to heavy industrial manufacturing. Mastering these principles provides insight into the invisible infrastructure supporting modern medicine, advanced research, and global telecommunications. The entire system operates on a single concept from quantum mechanics, known as stimulated emission. The process begins with atomic excitation. An external energy source bombards a material, forcing its resting atoms into a temporary higher energy state. When a photon strikes an excited atom, it forces that atom to drop back to its resting state, releasing a second, perfectly identical photon in the process. One photon becomes two become four. This duplication creates an exponential cascade of synchronized light within a closed system. Left alone, this chain reaction dissipates. Harnessing it requires specific hardware to contain, reflect, and direct the multiplying photons into a coherent stream. The required hardware relies on three core components. The first is the energy source, or pump, supplying initial power. The second is the gain medium, the physical material that receives this energy and amplifies the light. The pump fires constantly, keeping atoms continuously excited. The third component is the optical resonator. By placing mirrors at both ends, the trapped light reflects back and forth, growing denser and more powerful with every pass. Together, the pump, medium, and resonator force chaotic energy into an amplification loop, continuing until the light escapes through a partially transparent mirror. The escaping beam exhibits three properties. First is coherence. Individual waves perfectly lock in phase, aligning into a unified front. Second is monochromaticity. Exactly one specific wavelength, producing a single color. Third is directionality. Aligned photons travel parallel, maintaining a strict, straight path. Because the beam remains coherent, monochromatic, and directional, it carries concentrated energy and precise data over immense distances without losing physical structure. While the hardware triad remains constant across designs, changing the specific material used for the gain medium alters the laser's physical output and industrial purpose. Solid-state lasers, using materials like ruby crystals, and gas lasers containing helium-neon or carbon dioxide, deliver extreme thermal power for high-precision operations. Semiconductor lasers, or diode lasers, rely on miniature components. Their small physical footprint makes them the standard for integration into everyday consumer electronics. Fiber lasers pass light through rare earth-doped optical cables. This configuration operates with high electrical efficiency, driving heavy industrial tasks like robotic welding. These fibers also form the physical foundation of global telecommunications. They translate light pulses into digital bits, routing data across high-speed internet networks. The decision of which gain medium to use dictates the system's scale, determining whether the device reads a compact disc or slices through metal plating. Applying these different configurations to specific industries yields a wide array of capabilities. In healthcare, precise beam control enables exact corneal reshaping, safe tumor removal, and targeted skin treatments. In heavy industry, focused thermal intensity allows manufacturers to slice dense metals, weld aerospace components, and construct complex geometries using 3D printing. For scientific research, the predictability of light waves allows physicists to execute highly controlled spectroscopy, study atomic interactions, and measure vast orbital distances in space exploration. In daily public life, the technology automates grocery store barcode scanners and precisely binds toner to paper in office laser printers. By providing a reliable method to control light, laser technology operates as a foundational utility for modern infrastructure, functioning with the same essential ubiquity as the electrical grid. Implementing these systems provides strict advantages. Operations execute with microscopic accuracy, materials process at high speeds, and yields almost zero physical waste. However, these advantages come with operational constraints. Hardware installation carries high initial capital costs, systems demand skilled ongoing maintenance, and the focused thermal energy presents severe safety risks, including instant eye damage and physical burns. Despite these limits, development continues. In the immediate term, autonomous vehicle navigation relies on LiDAR systems to scan geometric environments with rapidly sweeping light pulses. On a longer timeline, laser arrays serve as the ignition mechanism for experimental fusion energy reactors, while phase-controlled light operates as a key component in early quantum computing architectures. Controlling the quantum behavior of photons provides a scalable mechanism to cut, measure, and transmit data. As material science improves the efficiency of the gain medium, the capacity of these systems will expand to meet the next generation of engineering demands.